So let's start today's lecture.
Sir,
Yes.
sir, I have also tried to do coding for that, so, but sir, my program is not running, sir.
So that's the natural thing to do, natural thing to expect. Uh,
So can I show you, sir? What's the? I am unable to understand what error they are telling about because I am very beginner in coding, sir.
hey, I would request all of you to not waste the lecture hour in discussion of your problems with the homework assignment. Right? As it is, we are very hard pressed. I mean, interaction in this video link is rather difficult, and accessibility is also limited. So, make the full use of whatever interaction opportunities you have, and whatever questions you have, you can always call me up. I mean, ठीक है. If you don't
So I have
if you don't have my phone number, here it is. You can call me up, you can send me an email, your problem, whatever you are facing, and we'll take it up.
So I have also created the discussion forum on Moodle page. If they want, they can use that as well.
Okay, great. So,
The first link is the discussion forum on the Moodle page, first link itself.
good. So, make use of that, and I mean, discussions are always welcome. My only request is please, I mean, as long as it is general discussion related to whatever we are discussing in the class, most welcome. But if you have a specific problem related to your assignment, tutorial problem, I would rather prefer to have it one-on-one. Let us not waste the class time for discussing individual problems. Is that fair enough?
yes, sir. Yes, sir. Okay, sir. Thank you.
Okay, fine. So, we were discussing about the, what were we discussing? Let me look at it. Yeah. So, lateral load resisting elements. So, essence of earthquake resistant design or earthquake resistant construction is that you need to resist the deformations in a horizontal plane, and for that you need to incorporate some strength or some kind of resistance in the lateral direction, horizontal direction, right? And that is not automatic. You need some kind of intent during the design process. So the right word is lateral strength requires engineering intervention. What does this mean? Gravity load comes, resistance to gravity load comes naturally. As long as the material doesn't crush under its own weight, you take care of the compressive strength, then it will support the weight, whatever comes onto it. But it is in the lateral direction that you need to really bring in your all engineering expertise, all your strength of material, engineering mechanics background to see and factor in this kind of resistance to her lateral forces coming onto horizontal plane forces or deformations, and which are to be resisted by the vertical load carrying members, vertical members, right? And that requires engineering intervention. So what are the lateral force resisting mechanisms? So what are the options? One is, of course, ubiquitous moment resistant moment resisting frames. You can have both RC or steel. So moment resisting frames you can construct either in reinforced concrete or in steel, or it can be some part reinforced concrete, some part steel, or it can be hollow steel sections filled with concrete, that is also possible, and so on. So there are various possibilities. So and then the critical part here is connections. Connections between beams and columns are critical. Right? Because the lateral force, when it comes on the frame, then it has to be withstood, or it has to be resisted by developing internal forces, and that is only possible by, unless if the members are able to generate and transfer moments between beams and columns. If the moments are not properly transferred, then it may lead to excessive deformations, and the performance objectives may not be met fully. Then as I have been telling you since last couple of lectures, that for earthquake resistant design it is essentially deformation control. We need to control the deformation. Earthquake imposes deformation on the structure, and the primary objective is to control the deformation. And then the deformations come in the lateral direction. So what is the best way to control the deformation in lateral direction? Please tell me, how does a beam develop its resistance to transverse loads? Can anybody tell me? I'll just take it as an aside. Maybe develop its resistance to transverse load. So what I mean to say, that you have a beam, let's take the simple case, simply supported beam with a mid-span loading, right? So how does this beam resist this load? What causes it to resist this load?
Sir, it resists the load by bending action.
Yes. So it will respond by this kind of deflected shape, right? So this is how it will deform, almost like a half sine wave. And then but then how do I control this deformation? What is it in the beam that allows us to control the deformation? If this deformation is excessive, throwing an hypothetical question at you, thought experiment. What if this stresses, bending stresses developed due to this deformed shape are under the limit, whatever limit we are looking at, right? So there is no concern about the limit states or the ultimate moment capacities being exceeded, or stress elastic limit or allowable limit for stress in bending or shear stress being exceeded. So they are all very well within the range, right? But the deformation, this deflection is too high. Right? So how do I control this deformation, maximum deflection?
So maybe by limiting the span.
Span is something that is not in our hand.
Then we can increase the I, moment of
Yes, you increase the moment of inertia, or in other words, you try to increase the flexural rigidity. Make the system be more rigid. Increase. What you try to do is increase flexural rigidity. Right? That is Young's modulus multiplied by the moment of inertia. Now material is same, so Young's modulus you cannot do much. The only way to do that is moment of inertia. And what is this moment of inertia? I is equal to third power cubic varies as third power of depth. Right? Moment of inertia varies as is proportional to the third power of the depth of the beam. So if you increase the depth, you will, the benefits are exponential. And that is what we do when we do this. We call use shear walls. So what is shear wall? Shear wall, if I draw tall buildings will typically have this shear walls. So this entire thing is reinforced concrete. In between you may have frames connecting with shear walls, so on. Right? So if you look at the earthquake load, let's say if I say this is the earthquake load, lateral horizontal force, then this force is transverse. If I look at it, it's a cantilever beam, inverted rotated cantilever 90 degree. So this is a cantilever beam, and if I use this shear wall, then the shear wall acts like a beam with a very, very large depth, and that makes it very, very rigid in deformation. Right? So it offers a very great degree of resistance to lateral deformation transfers to its axis. Right? So this is one of the very effective mechanisms of resisting or developing resistance to lateral loads, and often it is used in combination with moment resistant frames, and most commonly, I drew it here at the center of the frame. Most effective of placement would of course be at the periphery, along the periphery of the plan, but that doesn't really serve much of a purpose, functional requirement. This is very conveniently housed by converting the lift course, elevator course, as a reinforced concrete walls, and that can be integrated, so both functional requirements and structural requirements can be met to a great deal, right? So the critical point is it has to start from the foundation level itself. Shear wall, for a shear wall to be effective, it has to start right from the foundation level, and the foundation, it is not really a good idea that part of the foundation, if the location is such that part of the foundation is on the rock and part of the foundation is on the soil, that is something to be avoided. If it cannot be avoided, then of course it's a special case and very careful considerations need to be taken, so that to avoid any differential settlement between different parts of the structure or foundation. So once that is taken care of, then it is essential that this shear wall should rise from the foundation level. Many a times you will find that sometimes the shear wall is curtailed at this level, I mean basement parking or whatever, you need the complete spacing, open spaces there. So sometimes you will find that it is only, shear wall is only erected from the first floor or second floor, level 2, and this is all made clear, or even the columns, maybe the columns are there, or so this causes another problem. I mean, this is what we call as this, if this happens, then this causes what is known as soft story. Structure at the level above this is very rigid by virtue of this shear wall and lateral resistance. Even you may have infill panels here, and then the ground floor or the basement, whatever you have, it may not have as much stiffness as the upper floors. Then in response to this lateral load that is coming onto it, this entire structure would deform. I mean, very little deformation in the upper floors and steep deformation at the soft story, because the lateral stiffness is very small for this particular frame. And then this kind of deformation usually are not accounted for, or the structural elements are not able to undergo or absorb this large deformation, and the entire thing collapses. The entire structure, I mean this floor will simply get crushed under the weight of the floors above, right? So shear walls are very good system, but care has to be taken that it has to go right at the foundation level, and the entire structure. The other care that you need to take is, I have been emphasizing about this, minimize eccentricity, between center of mass and center of rigidity, right? And that is possible by playing with the structural elements, the shear wall placements, and the frame proportioning, right? And of course the placement of the mass. Another point is, if we can minimize this eccentricity, then lots of difficult problems arising because of the torsion can be eliminated, because what happens during torsion is it imposes additional deformations at the corner columns or the columns at the periphery, or the structural elements, lateral load resisting elements at the periphery. and if those have not been designed to accommodate those, sometimes it may not be possible to accommodate these large deformation, because these additional deformations because of the torsion, they are in addition to whatever deformations the frames will undergo under the influence of this horizontal load or horizontal deformation that is imposed by the earthquake on the system, right? So this combined deformation may be beyond the capacity of the structural elements, and the entire thing will collapse. So I keep saying about collapse, but we don't really allow it to collapse. I'll come to that little in a little while. So moment resisting frames, shear walls, minimize eccentricity, so that is configuration, appropriate structural and architectural configuration. Right? And then we have this weak zones or intentional weak zones. So capacity design, the idea is preferred mode of failure. So preferred mode of failure so essentially what we are talking about, weak beams, strong columns, and shear capacities has a larger factor of safety, because shear failure is a brittle failure. It doesn't give any warning, and the entire thing will lead to cascading system set of failure of all the elements. So we do not allow. So even if the shear beam has to fail, it has to fail in or the capacities have to be exceeded in beams only in flexure, not in shear. So bending capacities, it will exceed. We allow the hinging to take place only in flexural mode, not in shear mode, right? So shear failure is absolutely no. We never allow that to happen. If something has gone wrong in shear, then it's most probably a design flaw or some kind of neglect somewhere. So somebody has not been careful enough in taking care that shear capacity has a larger factor of safety. You should never be able to achieve this limit state of shear in a normal course of design, right? You should always have, the limit state of bending should always hit first before you go anywhere near the shear capacities. So then another point that I have been talking about is the energy balance. Energy balance during earthquake, right? So I had mentioned about kinetic energy, plus elastic strain energy plus dissipation energy has to be greater than or equal to earthquake input energy, right? So for a given earthquake motion, you have some finite earthquake input energy, and these are the capacities. So this is the demand, energy demand imposed by the earthquake, and these are the capacities. And at any instant of time, I mean, all these keep on changing. Kinetic energy keeps on changing with time, strain energy keeps on changing with time, this dissipation, energy dissipation also keeps on changing with time. So at any instant of time, sum total of this should be greater than the input energy. If that happens, then the structure should be able to survive without collapse, right? So kinetic energy is something that you do, I mean, with the material that you put in, whatever inertia properties, mass is there, it will have its own kinetic energy. Strain energy by elastic mode of elastic deformation, whatever strain energy is stored. So there is a finite limit to which what we can do here. But if we wish to have capacity or resilience built into the structure, then we really need to invest into this energy dissipation capacity. So this is the key for energy dissipation is the key for developing seismic resilience. Resilience is the term for the property of anything, any system, that recovery, how fast is the recovery after some mishap, right? So if we wish to develop any society, I mean, resilience can be a society, it can be a person, even a structure can be thought of as a resilient system. So the idea is how soon after a major earthquake strikes, how soon the structure can recover from that and get functional and start discharging its normal duty, normal function, right? So if we are looking at developing seismic resilience, ideally we should have seismic resilience in every system that we build. So this energy dissipation capacity is the key. So now what is the energy dissipation comprising of? So energy dissipation, you can have hysteretic energy dissipation, or damping. So for hysteretic, it is the structural response. This entails or I should say, let me be more specific. Structural response in inelastic range. And damping, it can be inherent damping of the material, every system has some kind of loss mechanism. So no system is 100% energy efficient. So any conversion between potential energy to kinetic energy, it is not possible to have 100% conversion. some part of energy is always lost, and that is the inherent damping. Then we can have supplemental dampers. In addition to the inherent damping in the structure, which is generally very small, not really a great amount of energy can be dissipated for most of the common structural materials that we deal with. So, by virtue of damping. So, that is not a large amount of damping that is available, inherent damping. But we can talk about supplemental, we can add special devices which will dissipate energy, and those are called supplemental dampers, and there are several mechanisms of doing that. We can just add some kind of friction plates. During vibration, plates would slide against each other, and that will cause some dissipation of energy during vibration. We can have some kind of shock absorbers. I mean, all of you are familiar with shock absorbers of one kind or the other. The suspensions that you see under the automobiles, those are essentially supplemental dampers, and that take care to absorb the shocks, and they are not allowed to pass on to the rider, so that the suspension is designed to improve the comfort index or ride comfort level of the ride comfort of any vehicle. So similar kind of system can be incorporated in structural systems. I mean, so those are called supplemental viscous dampers, and it is possible to deploy them. But deployment is another issue. It will be it interferes with architectural functional requirement and so on. So those are other peripheral issues that need to be dealt with for supplemental dampers. But this is always available to us. First thing, because most of the time, as I said, earthquake is a very rare phenomena, and chances are that a structure may outlive its intended design life without witnessing any earthquake whatsoever, right? Or it may be forced to experience several earthquakes in a row, large earthquakes in a row. I mean, it's such an uncertain thing. So it is not physically, or it is not economically viable to withstand all the earthquakes, even if it is a design basis earthquake, whatever is the design basis earthquake we design. It is not economically viable to withstand that earthquake for elastic behavior. With elastic, I mean the structure to withstand that intensity of ground shaking with complete elastic response. We can do that, but it is going to be costing some money, and money is a very sensitive point. Why we put money on something that is so random, right? So but life is of course precious, cannot be valued in money terms. So the emphasis is, even though we allow inelastic deformation in the structural system, we should not allow any loss of life. And then how do I enhance? And that is only possible when I am able to, I can design a system where I can dissipate large amount of energy which is coming from a large intensity earthquake, right? So if I am able to dissipate large amount of energy, then it provides me enough safety cushion in the structure which will allow me to save lives. So the idea is, if I try to define it in terms of load deformation behavior, so this is elastic, right? So this is what I can say, elastic range. After that, this is inelastic, and this is, let's say, ultimate deformation. So delta u, this is delta y, elastic deformation. So ductility mu is defined as ultimate deformation divided by the yield deformation, the maximum elastic deformation, right? So if I have large ductility, then this kind of hysteresis energy, I have more access to hysteresis, energy dissipation via hysteresis. So high ductility is highly desired. Now the question is, how do I achieve high ductility? So that the ductility is a desired property is all very well, and probably first thing that we need to understand that I cannot have ductility unless the material is ductile. If the material itself is not ductile, then there is no question of developing any ductility in the structure. So the material has to be capable of having this kind of load deformation curve which can give us ductility. Now there are two different things that we are talking about here: ductility at a material level or the element level, and the ductility at a structural level, global level, right? So these are two different concepts, and although it is easier to talk of ductility at the element level or at the material level, but what is actually being put in practice is the ductility of the complete structure. It is the complete structure which is withstanding the earthquake, not a particular section of the material, right? And then there can be several things in which, for example, let's say reinforced concrete. So how do I make reinforced concrete behave like a ductile material? Most of the time you will find reinforced concrete would just have very small yield and then immediately drop off, right? So this is what is a brittle, and this is ductile. So we should try to make systems, material that we are using, the construction material, this from which the structural elements are made out, to be as ductile as possible, and therefore we have a spatial confinement, reinforcement confinement, or this is possible. Reinforced concrete, we have spatial ductile detailing provisions. So reinforcement, only by suitable placement of reinforcement or a particular prescription, that if you use reinforcement in such a way or take this care, this set of precautions when you provide reinforcement, then the section has better behavior as far as ductility is concerned, right? And that is what is incorporated in IS 13920 ductile detailing. I have uploaded this code in the LMS site, Moodle website for the course. You can have a look at it. Another code that I have uploaded is the basic course for earthquake resistant design 1893. part 1. Part 1 is for buildings, and that is what we are going to be discussing in this course, right? So I would request all of you to please read this 13920. That's very important and critical for developing this ductile behavior, making reinforced concrete sections ductile in bending. Remember, I am always referring to plastic hinges or inelastic deformation in the beam only happening in the case of bending, right? So it is when I talk of ductility in of reinforced concrete section, I am always referring to ductility with respect to bending deformations, right? So how to make bending deformations in beam sections more ductile? So that is the idea. So you can I strongly recommend all of you to please go through this code. It's a very small document. It should not take you very long to read and understand the provisions, and we will start our next session on from this point. Thank you.